Okay, let's talk about Newton's method. And then we'll come back around to the other stuff. It's not that bad. All Newton's method is, it's a way of estimating the solution to an equation. An equation specifically equal to 0. Sometimes this gets phrased in the following way. So I'm going to kind of start this off just kind of how I would think of it. So for example, I want to use Newton's method to estimate square root of 2. Which might seem kind of like a backwards way of saying what we're about to say, but it's a perfectly fine place to start. So what you really want to do if someone says something like this is say, well, okay, what I'm really trying to do is I'm trying to find a solution to an equation. So what's square root of 2 the solution to? Well, there's a lot of answers to that question. One of the real, maybe the least creative answer would be x minus the square root of 2 equal to 0. Technically, that would be a solution. But the one I'm really looking for is we're trying to find a solution to, or estimate a solution to x squared minus 2 equal to 0. Because the square root of 2 is a solution. So is negative root 2, but we won't worry about that. Okay, let's see how good my picture drawing skills are. I think, yeah, let's get another picture. So here's the idea. Here's the geometric idea. This is not how we calculate it, but here's the geometry of what we're actually doing. So we're saying, okay, great. X squared minus 2, I can graph that. Y equals x squared minus 2 is just your usual parabola shifted down by 2 units. I'm trying my best to make a nice graph here. Yeah. So normally I would say, you're probably not going to get it phrased like this, although I've seen it phrased like this. Another way someone could have phrased this question would have been to have said, use Newton's method to estimate a solution to the equation x squared minus 2 equal to 0. Which is what we're doing. But sometimes people like to phrase things in different ways to get a different meanings. So here's my parabola drawn as well as I can draw it. And I'll point out right there, that's where my actual solution is. Right, there's x equal to approximately the square root of 2, 1.41 something. Okay, here's what we're actually going to do. We're going to make a guess. I'm going to guess usually the closest whole number I can pick. Sometimes it's the closest fraction I can pick, whatever. So my first guess is going to be x, and I'm going to say x of naught because we usually use this subscript notation to indicate further guesses. 1. I'm going to guess 1. Okay, now check this out, because here's where the geometry is happening. We'll talk about how it becomes a formula. From my first guess being 1, let's zoom in here so you can see this better. So there's my first guess at 1. We're going to go down to the function right there. That point is 1, -1. And then we're going to draw the tangent line to the graph at that point. So I know at that point well, let's see, the derivative of this is 2x. If I plug in 1, the slope would be 2. So I'm going to go over 1 over 2. I'm best to draw this line. There's my tangent line at the point 1, 1. And now look, this new point where we're intersecting, that's our next guess. So there's my x1. And then the idea is you basically repeat. I'm not going to draw more on this picture because it'll just start to look gross. But the idea basically is then you repeat the process. So you take your new guess, you find the function value, you draw the tangent line at that new place, and then wherever the tangent line crosses the x-axis, that's your next guess. And you just keep iterating this iterative process until someone tells you to stop, or until you've gotten close enough of the process. I don't know when to stop. So here's how this calculation actually works. And I'm literally going to have to derive it because I don't remember how it works. So here's what I want. I want to find out where this tangent line is crossing the x-axis there. So I'm going to find the equation of this tangent line and then set it equal to 0, I guess. Okay, so just hold on for a second. You might not want to write this down just for a second. So let's do this very generally and then we'll do it very specific. So this tangent line here. Well, the slope, how do we find the slope of the tangent line? Yeah. So my slope is going to be f prime of x naught. I'm going to write this very generally so we can see the formula, and then we'll do it very specifically. And then the coordinate there, that coordinate is x naught comma f of x naught. Right? I plugged in my first guess, and the y value is the function value. Okay, I know how to find the equation of a line. It's y minus the y coordinate equal to the slope times x minus the x coordinate. Or in this case, y minus f of x naught equal to f prime of x naught times x minus x naught. That's the equation of this red line. And I could solve for y, I guess, if I really wanted to. I don't really want to, though. So here's the deal. I want to find this new point here. At that new point there, I'm calling the x coordinate x1. What's the y coordinate there? At that new point. Yeah, that's fair. But let me point out, what's the y coordinate of that point that is on the x-axis? So here's what we're going to do. We're going to plug in this x1 for the x value, x, and this y1, which is 0 for the y value. So here's what we're going to get. We're going to get 0 minus f of x naught equal to f prime of x naught times x1 minus x naught. And now we're going to solve for x1 because we're trying to get from our initial guess of x naught to our next guess of x1. So solving for x1, I'm going to divide both sides by f prime. So I have negative f of x naught divided by f prime of x naught equal to x1 minus x naught. And I'm going to add x naught. So x1 equals x naught minus f of x naught over f. Or more generally, the next guess for your x value is your previous guess minus f of your previous guess over f prime of your previous guess. So people often write something like x sub n plus 1 is equal to x sub n minus f of x sub n over f prime of x sub n. And that is how you just keep finding every subsequent estimate of your 0 or your solution, or whatever you want to call it. Questions about anything so far? Yeah, Justin. Yeah, this is the general formula for doing the iterative process of Newton's method. You can. I wanted to show you where it came from because it is kind of, it makes sense, right? Like you think about, but you should, yeah, you definitely shouldn't derive this on your test or whatever. I derived it because I literally didn't remember what the formula was. Like I'm like, I know it's a plus somewhere, but I don't remember if it's a minus or a plus. And I was just like, we should show the work anyway. But this is actually the formula. So back to our example here. If I just throw things into this formula, well, my x sub 0 was 1. My f of x was x squared minus 2. So I know that f prime of 1, sorry, f all fine. F prime of 1 is going to be 2 times 1, which is 2. And f of 1 is going to be 1 squared minus 2, negative 1. So throwing that all into my equation here, I'm going to get that x sub 1, right? My next guess is going to be 1 minus f of 1, which is negative 1, over f prime of 1, which is 2. Which is 1 plus 1/2, which is 1.5. Which is definitely a closer guess, right? 1.5 is much closer to what we know root 2 is approximately equal to than 1 is. And then we do it again, right? So then we're going to be like, okay, so now if I want to find x sub 2, it's going to be 1.5 minus f of 1.5 over f prime of 1.5. I would probably use fractions here, but I don't know. 1.5 squared is not that bad. It's 2.25. So here we're going to get 1.5 minus, let's see, 2.25 minus 2 is just 0.25. Again, 1.5 squared is 2.25. Divided by f prime of 1.5. Well, the derivative is 2x, so f prime of 1.5 is going to be 2 times 1.5, which is 3. And then things start getting terrible. This is equal to what? 3 over 2 minus 1/4 divided by 3 is 1/12. And then you can multiply this by 6 over 6 and get 17/12. But as you can see, maybe the further you go, the worse the numbers are going to get. And usually after a couple iterations, you typically have to pull out a calculator and start using a calculator to find the next things. Questions so far?
We're choosing 1.46.
Yeah, 1.415, I think, something like that. 17 over 12. Do I have a calculator? Of course I didn't bring a calculator. Why would you ever bring a calculator this class, James? 1712 is approximately 1.416. Good question. Usually they give you easy examples, if they're going to give you any examples. If you have to do a question like this, though, like, for example, let's say I had to do more iterations. Well, here's an easy way to kind of do more. Is this an easy way to do it? Let me think about this for a second. That might be easy. We'll find out. Here's what I think might be an easy way for. So I'm trying to calculate this thing where my function, so I would actually probably write out, I probably would write out the actual formula here, meaning my, it's very dark. So meaning I would say in this particular example, my x sub n minus f of x sub n over f prime of x sub n, where f of x is x squared minus 2. This is looking like x sub n minus x sub n squared minus 2 over 2 times x sub n. So that's what I'm thinking of. That's my next guess. So remember, my function is x squared minus 2. My derivative is 2x. So f of x is x squared minus 2. F of x sub n is x sub n squared minus 2. And f prime of x sub n is 2 times x sub n. So what you can do, I think, it's been a while. We can get that thing back here. You say, okay, well, that's kind of what I want to calculate. So I'm just going to write x minus x squared minus 2 divided by 2x. Cool. Which might not look very helpful, but here's the helpful part. Give yourself a table. Okay, here's my first guess. Okay, well, great. So 1.5. So here's my next guess. Great. Now, Come on, you don't want me to copy that? Garbage. Well, fine then. And oh, except not negative, James. So you can find subsequent guesses using Desmos relatively quickly by just doing this. And I feel like you should be able to copy that, but it's garbage, so I can't. You just keep plugging in the next number. So 1.41421337. So on. Now, sometimes the question will be, how many iterations do you have to do until your answer is correct to 2 decimal places? Well, after we do the, right? Well, if that's the first guess. I guess, yeah, this is the first iteration, the second iteration, right? The second decimal place didn't change. That means we're correct to 2 decimal places. Questions so far? So this is what I do when I have to like do more calculator work. I'm just like, well, let me just pull this up and start typing things in. It's not for exactly precise, right? Because technically I shouldn't be writing 1.4167. I should really be writing 17/12. And not just delete it. But look, it still gives me, if you write enough decimal places, you're going to be fine. So that is Newton's method in a nutshell. You are taking your first guess to this to find the solution of this equation, and this you're just plugging in more and more and more guesses. What else to say about this? So that's why. Sorry, I accidentally picked the literal same example, which is fine because it's boring. So there's not a lot more to say about Newton's method. Like, I'm trying to think, like, is there anything else to say about Newton's method? Not really. Okay, here. Sure, here's an example from the textbook that seems ridiculous, but we'll look at it anyway. This is problem 13 from section 10.6, Casey Karen. So approximate to 3 decimal places. The solution to 4 minus x equal to the natural log of x. Or the way this is phrased in the textbook, the x value where these two functions intersect each other. So they've done this, where they've graphed 4 minus x. And the natural log of x. That okay, estimate that point right there. So before we do anything, you want to make it all equal to 0. Right. So first step, bring everything to one side. I would bring everything to the left, to the right in this case. I like things being positive. I would rather have 0 equal to x plus the natural log of x minus 4 instead of negative natural log of x plus 4 minus x equals 0. I just rather would have less negative signs if I have a choice. Okay, so this here, that's our f of x. And then f prime is going to be 1 plus 1 over x. So the thing we're going to be calculating here is that our next guess is going to be equal to our previous guess minus f of, I always forget which one goes on top. So I think it's f, right? Let's look back at my notes. I literally, like, I know I just did it, but it's, I cannot. The problem is, okay, it looks like the opposite of what I feel like. I know I'm wrong. I want it to be f prime on top, but it's not. F of x of n. So in this particular case, it's going to be x sub n minus f of x sub n, which is going to be x sub n plus the natural log of x sub n minus 4. over f prime, which is 1 plus 1. If you don't like writing the x sub n's, you don't have to. You can just be like, yeah, it's x minus x plus natural log of x minus 4 over 1 plus 1 over x. And then just start guessing away. So this is certainly made to look like our first guess should probably be 3. Because the point of intersection looks like it's pretty close to 3. Okay, and then let's, oh my gosh, the first guess is going to suck. It's going to, right, I mean, or the next one, right? X1 is going to be 3 minus 3 plus the natural log of 3 minus 4 over 1 plus 1/3. That seems dumb. Here's what seems dumb about this to me. I don't know how you would do this without a calculator, like realistically. And I mean, first of all, natural log of 3 is something we have to approximate. You might know what that is. You might not. I think it's like 1.1. I actually don't know. But right, you have to use a calculator to do this thing. And then at that point, it's like, well, why wouldn't I just use a calculator to answer the question that they're asking in the first place? That they're doing using a calculator to use this process to answer the question. Like it just seems. But that said, we can still totally do it. If you had to do this question, you could be like, well, okay, great. I'm going to toss that whole garbage thing I just wrote in here. So it's going to be x minus x plus natural log of x. Where'd you go? Minus 4 divided by 1 plus 1 over x. Okay, and then our first guess was, I don't want to delete all these. Can I delete all of them easily? Yeah. So our first guess was 3. And then great. My next guess is 1.8. Okay, great. My next guess. I went too far. Don't type more decimals even if you think they repeat. I don't know if they actually repeat. They probably don't because there's a log in there. And so it looks like we're getting there. 1.4149899. We're there? We get 3? We did. Cool. So 1.414 is our estimate correct for 3 decimal places. Kind of interesting. Yeah, Justin. We wouldn't really, like, you don't. I have no, so to do this on an exam, realistically, the example has to be easy. And they'll at most ask you for like 3 iterations. And the first 2 might be relatively easy calculations, and the third one might be a little bit gross. That's pretty typical. I'll try and look for one later on. Maybe there's one on the practice final that I have for you. But yeah, there's not really much more you can do with that. Yeah.
For x of 1, can you just plug in x of 0 into xn plus 1?
Right. Well, because what I'm saying here is, if I let n equal 0, on the left side I get 0 plus 1, so x of 1. On the right side I get x sub 0 minus x sub 0 plus natural log of x sub 0. Typically, yes. Potentially not. So, for example, if I gave you a similar-ish kind of problem, saying, okay, I want to find or estimate the solution to x cubed minus 7 equal to 0. So let's write down our formula. Let's just write it the nice way. Let's say, so our next guess is equal to x minus f of x, f prime of x, which is going to be x minus x cubed minus 7, 3x squared. Okay, great. Now I want all of you to, on your own secretly, don't share your answers with anybody, write down what you think your first guess should be. Think about what number might be the best first guess you could make.
Your first guess is you really want to be whole numbers.
Yes. So here's my best first guess. My best first guess would be 2. Because I know that x cubed minus 8 has a root of 2, and this is just shifted from that a little bit. I might have picked a problem that's not going to be good though. Sometimes cubic things have issues. So sometimes Newton's method doesn't work. Let's take a look and see what happens here. I don't actually know what's going to happen here. Let's find out. So x1 is going to be 2 minus, let's see, 8 minus 7 over 3 times 4. It's going to be 2 minus 1/12. Seems fine. And then my next one, that's when things get gross. You definitely don't want to find the cube of that. So here's where I would like, right, I'm going to go, still do the same thing. Right, I guess I can write it out. 2 minus 1/12 is 23/12. So then my x2 is going to be 23/12 minus the 23/12 cubed minus 7 over 3 times 23/12 squared. That seems insane to calculate. So let's go ahead and take a look, just because I want to see if the thing that I think might happen is going to happen or not. Okay, let's back it up. Oops, okay, too much backing up. So now we're doing x minus, I'm just going to simplify this. X cubed over 3x squared is just x over 3. And minus 7 over 3x squared is plus 7/3 x squared. Oops, whoa, not like that. I'm just making it easier, right? But I want to point out to everybody, right? This literally is the same thing, right? I've got x and then x cubed over 3x squared. The x squared is canceled. You get an x over 3. And then a minus 7 is a plus 7 over 3. Oh, I did make a mistake. Small. It's a small mistake, but it's a big mistake. That x squared is in the denominator. That's what this thing looks like. Okay. What was our first guess? Okay. Fine. Let's do this. Great. There's my first guess. 2. And there's the number that is probably 23/12. 1.91. Yeah, that looks like divided by 12 when you got all the 6's up there. And if we plug in 23/12, okay. And if we plug in that, I wish you could copy that. I'm very annoyed that this is not a copy. It's wrong. 1.912938.5. Okay, looking pretty good. I think we're good to like what? 4 decimal places, 5 decimal places. Cool. All right, so you know what question we've answered here? We have answered the question, what is the cube root of 7 approximately equal to? Right, because if you solve this for x cubed equal to 7 becomes x equal to the cube root of 7. So we've just shown that the cube root of 7 is approximately 1.91 whatever. Which seems reasonable, right? The cube root of 7 should be a little bit less than 2. So I feel like that's a totally valid thing to see. Okay, so I think that's enough about this process, which I've forgotten the name of. Thank you so much. Newton's method, Newton's law. I think it's actually Newton's method. Newton's law, I think, is something else. Right, there's lots of, Newton did a lot. Okay, big deal. Let's go back and talk about the Taylor polynomial remainder estimation stuff, because that stuff is a pain in the butt as well. Where'd you go? Examples. One second. Yeah, so this is basically called Taylor's remainder. So let's look at the kind of general, so let's remind ourselves what Taylor's formula is. Taylor's formula says your function f of x can equal, okay, I'm gonna write out a few things here. F of a plus f prime of a over 1 factorial times x minus a. And then I'm gonna write a few more terms. Actually, I'm gonna write the nth term out here. So it's gonna be the nth derivative of f at a. I should point out, when you're writing an nth derivative, you should write the n in parentheses like that. You don't write the parentheses there. You actually mean you're raising that function to the nth power, which is a different thing. Over n factorial times x minus a to the n plus the next derivative at a over n plus 1 factorial times x minus a to the n plus 1. And go on and on and on. And so what you can do is, well, if this is what your function is equal to, you can use that to plug in any x value you want to actually evaluate it somewhere. So for example, we could plug in x equal to 1 or to 0. I should say, we can plug in any value of x that's within the interval of convergence. And so if this thing only converges when x is between -1 and 1, you can only plug in values like a half or a third or -2/3, something like that. This is just Taylor's formula. So what we're going to do is we're going to say, this is going to be the nth degree Taylor polynomial. And this part over here, all the rest of the terms forever and ever and ever, that is the nth degree Taylor polynomial remainder. You write as Rn of x is remainder. Or you might also call it the error in the estimate. Because if we're using the nth degree Taylor polynomial to do an estimate, whatever's left over is your error. Okay. And so here's where we're just going to throw a theorem at you and be like, we're going to believe this is true because it's true. We're not going to justify it because it's a pain. So there's a theorem that says all of these terms. Well, we can say that all of those terms, whether or not they add up to be positive or negative, we're going to take their absolute value. And whatever they add up to in absolute value has to be less than or equal to essentially what I think of as the first term of this. But there's a very, very small difference. The difference is this. I'm going to write the absolute value of the n plus 1 derivative at some z value, not a, times our x minus a to the n plus 1 power divided by n plus 1 factorial. And there's a condition on z. Z must be between your center and whatever x value we're plugging in. And so x is going to be replaced with whatever number we're actually trying to evaluate this thing at. And then z is somewhere between. Now here's the thing. You're never going to know what z is. What we're going to do is we're going to say that, oh, you know what? Sorry, I made a tiny mistake here. It's not that big a deal, but it's kind of a big deal. Really, this is actually equal. It's not a less than or equal to. This is actually an equality here. Apologies. But then what we do is we say, well, since we never know what this nth derivative z is actually going to equal, we're gonna find an upper bound for it. So we're going to say that this is going to be less than or equal to, people often use the letter capital M here, times x minus a to the n plus 1 over n plus 1 factorial, where capital M is the maximum value of that n plus 1 derivative, where z still has to be between a and x. And it can be actually equal to a or equal to x. That is definitely an option if that is what helps us find the maximum. So that's the idea, is that to get a bound on the error, we're going to get a bound on this quantity there. Okay. So let's use a very kind of typical example. I'm going to use a third degree Taylor polynomial to estimate sine of 1. Why not? 1 radian, by the way, sine of 1 radian. Which is kind of funky. Where is one radian? How much is 1 radian? How many degrees is 1 radian? What even is 1 radian? Well, let me ask you a different question. How many radians around the whole circle? 2 pi. 2 pi radians, right? Because literally what a radian is, it is saying how much angle you get when you go 1 radius length along the circle. That angle is 1 radian. And it's close to 57 degrees. I always think of it being close to 60 degrees. And I know that sine of 60 degrees, I should have done cosine, oh well, is square root of 3 over 2. Okay, so I'm going to use a third degree Taylor polynomial here. So here's my Taylor polynomial for sine of x is equal to x minus x cubed over 3 factorial, and I'm going to stop because that is right. That's my third degree Taylor polynomial for sine. I don't want any more terms because any more terms would get me a higher power. This is a third degree Taylor polynomial. Okay. So if I plug in 1, sine of 1 is going to approximately be 1 minus 1 over 3 factorial, which is going to be 5/6. Which is, I want the decimal here just because I want to say what it is. Let's see. I should know the decimal for this. 0.16, so 0.833 forever. The reason I want to point this out is because the square root of 3 over 2, which is what sine of 60 degrees is equal to, is approximately, I really love this calculator so much. I'm sure it's not sarcasm in my voice there. Is 0.86. So looking at this, sine of 1 radian, which is pretty close to 60 degrees, the value here, yeah, it's looking like it's pretty close to what it should be, which is comforting. So now the thing we want to ask is, what is an upper bound for the error? Well, we're going to say that this is our third degree Taylor polynomial, P3 of x. And so our remainder, R3 of x, is just given by the absolute value of the next derivative, so the fourth derivative of my function, times x minus my center. What was my center that I never ever said? Yeah, 0. How do we know it's 0? By the way my Taylor polynomial is written, right? Looking at that, I have x minus 0 minus x minus 0 cubed over 3 factorial. Usually if someone is asking to use sine, we are automatically just centering it at 0 because that's the typical way to do it. Same is true for cosine and for e to the x and for 1 over 1 minus x. Okay, so x minus 0 to the fourth all over 4 factorial. Okay, oh, sorry, I made a tiny mistake there. That should be f to the fourth of z, not x. What's the fourth derivative of sine? It's sine, right? Remember sine and cosine, they repeat every 4 derivatives. So if you start off with a trig function, sine or cosine, said someone says what's the 4th derivative, that gets whatever you started with. Not true for any other trig derivatives, right? But sine and cosine. So this is going to equal the absolute value of sine of z times x to the 4th, or 4 factorial. Okay, but I'm actually trying to find the remainder when x is equal to 1. This is really R3 of 1, which is going to be still sine of z times 1 to the 4th over 4 factorial, or just sine of z in absolute value over 24. And z has to be between my center, which was 0, and my x value, which was 1. And here's what's great about sine and cosine. Oh, question, Justin. Josh, sorry. Because z is a number we don't know. Here's what the theorem says. The theorem says there is some value z between a and x where the remainder actually equals just this one thing, but we don't actually know how to find that z value. So here's what we're going to do. We're going to say, well, I'm just trying to get an estimate of how big the error can be. I'm not actually finding the exact error. We are getting an upper bound by saying, well, our error is for sure at the most this much. So what we do is say, well, sine is especially nice, and so is cosine, because we know that no matter what you're plugging into a sine or cosine function, the biggest output you can get is 1. So I know for sure that no matter what z ended up being between 0 and 1, this is definitely less than or equal to 1 over 24. So for sure, my error is less than 120, less than or equal to 124. So that is the Taylor error formula, which is this one back here. It's the sorry, it's somewhere. Oh, sorry, it's over here. It's the Rn of x is equal to the next derivative at the unknown place z times x minus a to the n plus 1 over n plus 1 factorial. They go hand in hand. So I mean, if you're being asked to estimate something, you are using a truncated Taylor polynomial, right? You're not using the entire thing because that would go on forever, and you'd be actually just finding the value. But the idea here, so here's a good example. Is that a good example? No. Another kind of typical example is estimating like e to the something. So let's say I want to use a 3rd degree again. Sure. Sure. 3rd degree. Why not? 3rd degree Taylor polynomial. Centered at 0. Yes, of course. Sorry. Thank you. To estimate e to the negative 1. Which, knowing that e is close to 3, e to the negative 1 should be close to 1/3. Okay, so here's my 3rd degree Taylor polynomial for e to the x. E to the x is 1 x squared over 2 factorial x cubed plus x cubed. I really should use an approximation here, right? E to the x is approximately this 3rd degree Taylor polynomial. And so that means that e to the negative 1 is approximately 1 plus negative 1 plus negative 1 squared over 2 factorial plus negative 1 cubed over 3 factorial, which is equal to, the 1's cancel. I've got 1/4 minus 1/6, which is going to be what, 3/12 minus 2/12, so 1/12. That seems not right. Seems really not right. 1/4 minus 1/6. Yeah, I guess this is not a very good estimate. here's why it feels really, really not right to me. I know that 1 over e to the negative first is about 0.3 something. 1/12 is really less than that. So sometimes your estimates aren't very good using this, unless I'm making a mistake, but I don't think I am. Right? This is definitely the right Taylor polynomial for e to the x. 1 plus x plus x squared over 2 factorial. Oh, I am. Thank you. Yes, I just saw it as well. Good call. Because I probably squared the 2 as well because I was doing something bonkers. Okay, that's why it's so context here. That's why it's good to think about what your answer should be, right? I knew my answer should be of 1 over e, which is close to 1 over 3, and my answer was too far from that. I was like, well, that seems wrong. So then if we do this, we get 3/6 minus 2/6, which is exactly 1/3. Sorry, oh my God. Is my brain ever going to work right here? 3/6 minus 1/6 is 1/6, which is 2/6, which is 1/3. Goodness gracious. Okay, so that's our estimate. Good estimate. What's our error? Well, the actual remainder would be all the rest of the terms. It'd be x to the 4th over 4 factorial, plus x to the 5th over 5 factorial, plus x to the 6th over 6 factorial. Which in this case, if you plugged in 1, would actually be 1 over 4 factorial, negative 1, minus 1 over 5 factorial, plus 1 over 6 factorial. But again, the whole idea here is that we are going to approximate this. We're going to say, well, we know that R3, I should say R3, this is R3, not R. R3 of x here is going to be my 4th derivative evaluated at z times x minus my center to the 4th power over 4 factorial. Okay, but what's my 4th derivative of e to the x? Well, t to the x. E to the z. I think we're going to get the same remainder here because, or the same error, which is fine. So here, what's going to happen is e to the z, if z is between -1 and 0, right? My x value and my center, and I want to make e to the z as large as possible. What do you plug in? -1, 0, or something in between? Right, we plug in 0. We plug in the rightmost point because we know that e to the z is an increasing function. Right, think about the graph of e to the x. It definitely goes up from left to right. So you always want to pick the rightmost value to plug into it. So you make that thing as big as possible. And that's going to actually happen a lot with these error questions, is the function you are trying to maximize will often be something that's either always increasing or always decreasing. So you either pick the right or the left endpoint to maximize it. So here, we're going to say this is less than or equal to e to the 0 times x to the 4th over 4 factorial. All right, I forgot to plug in the x value. So my R3 of 1 is going to be less than or equal to just 1 over 4 factorial. I'm plugging in the 1 for x. Should have picked a different number so the answer came out different, but oh well, it came out the same as the previous question. Sometimes that happens. And so what we're saying here is whatever 1 over e actually is, 1 over 3 is certainly within 1 over, is it within 1 over, oh my God, is it within 1/24 of that number? Talking is hard today, yes. I got it from just this right here, right? This is literally 1 minus 1, those cancel, plus 1 over 2 factorial minus 1 over 3 factorial is 6. The ones cancel, and I get 1/2 minus 1/6. 3 factorial, well, 3 factorial isn't 1/6. 3 factorial is 6. Exactly. Exactly. And 4 factorial is 4 times 3 times 2 times 1, which is 24. You're welcome. Yeah.
Just for a little more brief, how the R3 of X goes from the formula to each to 0 times 1 over 4 factorial.
So the difference here is I plugged in 1 for x. So R3 of x is the absolute value of x to the 4th over 4 factorial. I would say R3 of x is less than or equal to the absolute value of x to the 4th over 4 factorial. And then I'm subbing in the value of 1 for x. So I'm getting R3 of x is less than or equal to x to the 4th.
It's e to the 0
Because we wanted to make e to the z, right? We're trying to maximize
okay,
e to the z where z is between -1 and 0.
Oh, we're always trying to maximize.
Always trying to maximize that thing. Yes.
I was a bit confused, like why the sign have to change? That's fine.
Why is the what, Jake?
The sign have to change from equal to like less or equal to.
Well, because e to the z could be anything between e to the 0 and e to the -1. But if we're trying to maximize it, what we're saying is e to the z is less than or equal to e to the 0 on that interval. In fact, e to the z is less than or equal to e to the 0 for z between 0 and -1. That's what we're saying there. Would it be 1 or -1 for R3? Remainders are always positive. You can talk about what the error actually is, like if you're above or below. When we talk about an upper bound for the remainder error, we're always talking about the error being a positive number. Ooh. I see. Sorry, Brian's question was something different. Yeah, good question. Are we plugging in 1 or -1? We're actually plugging in -1. It still comes out to be the same answer, but yeah, good point, Ryan. Thank you. That should be e to the 0 times 1. Right, because -1 to the 4th is still +1. And even if it wasn't, we still be taking the absolute value. But you're right, we should definitely be plugging in -1, not +1. Yeah, Justin. 10.6? No, 10.5. 10.5, I think. I'll have to double check that.